Hello and welcome back. In this video, we're going to take a look at AP Physics question 2003, Form B, question 4. Let's take a look. In this picture, we see that there is a potential difference set up between two parallel plates. An electric field exists between these two plates. We are told that a beam of electrons of mass m and charge q and velocity v enter the region of a small hole at position A. The electrons exit the region through the plates between a small hole in B. Express your answer in terms of m, q, e, theta, and v. Ignore the effects of gravity. On the diagram of the parallel plates, draw and label the vector to show the direction of the electric field between the plates. Well, we can see from the picture here that the potentials have been established. Okay, potential difference has been established. This is the point of low potential, that's the point of high potential. And electric fields are always moving from high to low potential. So we would draw the electric field this way, with one E in there just to tell. Part A2. Draw on the following diagram, that means this right here, show the force acting on the electron after it enters the region between the plates. Well, the only force acting on this is an electric force, and that electric force is going down. That's because if this is the positive region and this is the negative region, then an electron that's fired into this region is attracted to a positively charged plate. Or you could say it's repelled from a negatively charged plate. Either way, it's forced down. Part 3. Show the trajectory of the electron as it that will exit the hole in position B. Well, this mirrors what we would see in a gravitational field. So if we took a baseball or took a soccer ball and we kicked a soccer ball and it had this trajectory through, it's experiencing a gravitational force and a gravitational field, right, that's acting so that the object accelerates downward the entire time. Well, this is mirroring that particular trajectory, because what you're seeing is an electron that's consistently repelled by this and attracted by this. In other words, electrons always go against an electric field. So you're going to see a similar parabolic trajectory, just like you would a ball on Earth. Part B. Determine the magnitude of the acceleration of the electron after it's entered the region between the plates. Well, if I see this, my first thought is Newton's second law. Newton's second law tells us that the net force equals mass times acceleration. The net force in this example is the electric force. We're going to set that equal to MA. But recall that the electric force is equal to Q times E. So we can rewrite this as Q times E equals M times A. And if we solve for A, we get Q times E divided by the mass. Part C. Determine the total time it takes the electrons to go from A to B. Well, it's essentially a kinematics problem, because remember, you have electrons that are going in one area and coming out another. Well, we are told that it has this angle, the velocity is entering this way, and there's an angle created here. Well, that's the same angle created here. So the velocity that it's entering from is going to have a positive component, and it's going to have a horizontal component and a vertical component. The horizontal component is v times the cosine of my angle. The horizontal component is v times the sine of my angle. Now, one of the things that we hopefully might recall is that the vertical velocity at the top is 0. There is no vertical velocity at the top. So two ways we could do this. We could take an equation like y equals y naught plus v naught yt minus 1/2 gt squared. Turn this into plus 1/2 at squared and solve the quadratic equation for time. We could do that. Or we could go vy equals v naught y plus a times t remembering, of course, that a is a negative. It's a negative acceleration, similar to the negative acceleration due to gravity. Okay, and we could solve for the time it takes to get to the top. In other words, the time here. But since time halfway equals time up equals time down, then simply multiplying by 2 will help. So time is equal to v naught y over the acceleration. Okay, and so that's the strategy that I'm going to use in this example here. Now, v naught y is v times the sine of theta, and a, we just found, was q times e over the mass. Okay, now, technically speaking, you'd be good enough to leave it like this, but you'd have to remember to multiply it by 2 because it's twice that time. So we could leave it like this, but just to kind of clean it up a bit, this is the same as 2v sine theta over 1 times mass over QE, which would simplify to 2mv sine theta over Q times E. Determine the distance between these two. Well, that could be solved by looking at this very similar to a projectile, in which case we would use v naught x times t. Now x is equal to d, the distance, and v naught x would be v times the cosine of the angle times all of that, which would be time, 2mv sine theta over QE. So if we rewrite this, we get 2m v squared sine theta times cosine theta all over Q times E. And lastly, in part E, now assume the effects of gravity cannot be ignored. How would distance d change for an electron entering region A and leaving at B? Well, quite simply, d would be less. Okay, and let's look at the picture above just to see. Right now, you only have the effects of an electric field curving that electron. But what if you had not only an electric field, but let's say you had two forces, a gravitational force and an electric force? Well, that would only mean that your electron would curve more drastically to the positively charged plate, meaning distance d would be less. And that is AP Physics 2003, Form B, Question 4.